Hello guys, welcome back to another video. Today is going to be kind of a finisher on last class. So we saw, well, I'll do a recap in a second, but ideally by the end of this class, you'll be able to evaluate the limits of rational functions when given an equation. So we'll kind of stray away from the graph a little bit, just to make sure we're comfortable by doing this algebraically. So when evaluating limits, let's recap what happened last class, because last class was really big on just computing limits. I brought in a special guest. He's a very busy man and runs a bunch of businesses in town. So hopefully, you learn something from him. He has a great business model, and he's very knowledgeable in math as well. So I will take it away. You can go ahead and come on. Yeah, go ahead and come on in.
Howdy there, folks. My name is Mr. Carmer. My granddaddy's name was Mr. Calculus. My daddy's name was Mr. Farmer. That's why they call me Mr. Carmer. Now, my my little buddy over here, Mr. Garcia, asked me to come in because I'm a big old math whiz, but also I'm a pretty successful businessman. I'm a farmer. I'm a I'm a wildlife exhibit runner and a manager. I own a haberdashery that sells miniature peaches for my kangaroos. And I have so many other businesses that I work 8 days a week, 40 hours a day. Now, that being said, y'all, I have loved what I'm doing, but I have missed the mathematics, so Mr. Garcia has came in to help me out here, and I'm gonna help y'all out. But gotta get these animals out of the way. These animals are always pesky, they're always busy, they're always noisy. Got here one of these little cats. Some people call me the male Carol Baskin. Not that Joe Exotic fella. Nah, got one of these other small cats, the big cat. Let's see here. I lost this thing, but I found it, thankfully. And I always have these rodents. These rodents just running around my farm, my wildlife exhibit. Man, these fake ratatouille looking fellas. Tisk. Well, today, folks, I want to talk to y'all about a little review of what y'all did last class. Now, I know y'all had this little fun thing called limit properties. Now, that's right, y'all talking about limit properties. Y'all had nine of them fellas. Had nine of them fellas. Alright? So these were important. Very important. Because this allowed you to compute limits while staying inside the laws of calculus. Now, here's the thing. When y'all did that, y'all noticed that there's something fishy happening. Now, y'all could just plug in x a for x, and y'all would have got the answer. And so, provided f of x is nice enough, y'all can say that the limit of x approaches a of f of x is just f of a. Now, we said that nice enough. Well, I mean, y'all said that nice enough last time was just like some fancy word for continuity. Fancy word for continuity, which is not a concept y'all will discuss. That's a later topic. But given that was a sorry that this chicken's being real annoying. Be real annoying that chicken. Now, folks, that's all enough y'all did last class. Now I think Mr. Garcia got some examples of what y'all did and how y'all can do this now. Provided f of x is nice enough that when it happens when you get a zero in the bottom when you plug it in. Alright, that's the question Mr. Garcia is going to answer. I got to get back. Those kangaroos and those haberdashers going crazy. But, folks, my name is Mr. Carmer. It's been a pleasure. Until next time.
All right, thank you again, sir, for coming out. Man, what a special guest we just had, guys. He's a businessman I look up to sometimes. If I ever have dreams or aspirations of running a business, I don't think I do. But thanks again. Just give him a round of applause there in your household. Some snaps, whatever other noise you'd like to make. So please, thank you. Please, sorry, I'm not a big fan of cats, so it's like, please leave. Okay, I think he's leaving. So, quick little recap again from Thursday's class last week. We learned these different nine properties, and I won't go into explanation of them again, but we learned that we can use these nine properties to compute limits algebraically. So, without having to rely on a graph, which is not bad because if I gave you this limit here, the limit as x approaches negative 2 of 3x squared plus 5x minus 9, and I told you to compute this. Sure, you can actually, if you wanted to, this isn't a bad one. You can graph 3x squared plus 5x minus 9 if you remember everything about multiplicity, zeros, all those things, if you and the vertex, all that fun stuff. If you knew all that, you can graph this by hand or with the calculator and take numbers on either side of -2. So numbers that are less than -2 that are approaching it, and numbers that are bigger than -2 that are approaching it. And you can do that and you can work it out and you'll see what the limit is uh, estimating to be. In this case, we're not going to use the graph. So again, this is just a recap. Excuse me. So what we did here again is we took these different properties and we actually used them to compute it. So property number 2 is saying that, hey, you can break it up if you have an addition or subtraction sign. We broke it up as 3 separate limits. Limit of our first term, limit of the second term, and limit of the third term. And next, property number 1 says, hey, you got a coefficient out front? Why don't you take that out? So we can take out the coefficient and place it in front of the limit. And now we're just evaluating the limit as x approaches -2 of x squared, and then limit as x approaches -2 of x, and then the limit of a constant. So from here, we're like, oh, well, 7 through 9 are our best friends here because what is it? Number 9 is saying, hey, limit of x squared, x to the n power, just plug in your a value. The limit of x, plug in your a. And the limit of a constant is just a constant, and that's what we did. We plugged in our a values respectively, and then we worked it out, and we got that the limit as x approaches -2 of 3x squared plus 5x minus 9 is -7. Again, if we wanted to, at the beginning, we could have done this by looking at the graph, going on either side of -2, and seeing that it was going to approach -7. And so with these, we saw, hey, that's a lot, but that's doable. Is there a shortcut? Remember, provided that f of x, my bad, f of x is nice enough. And when I say that word nice enough, I'm talking about this concept of continuity, which we won't discuss. But if your function is continuous, I can just evaluate this limit by plugging in my a value. Again, provided that f of x is nice enough. So given this next one, we're like, okay, well, how mean is Mr. Garcia? Does he hate us? Does he care for us? We're going to say right now that this limit here, that should be z. We're going to say that it's nice enough. Okay, we don't really know too much about continuous, but it's two polynomials on top of each other. That looks nice enough, right? So let's see here. If I was to evaluate this by plugging in 1 every place I saw z, so that's -2, I would get, is that 13? Yeah, be 13 over 6. Cool. That doesn't seem too bad. But let me just make sure we're good, right? Let me just make sure with those limit properties that when I actually evaluate this by plugging in my value of 1, I still get the same answer with the limit properties. So I think I have it. I do here. Nice. So again, it was number 4, I believe, number 4 or 5, that says that whenever you take the limit of a fraction, you take the limit of the numerator and the limit of the denominator. And now the numerator and the denominator just become like last time, like last example. We'll break it up. We'll take out those coefficients and then we'll evaluate them using properties 7 through 9. And so when we get that there, it's just going to end up being 13 over 6, which is what we just got. So that's pretty nice, right? Provided that f of x is nice enough, we can just plug in our value of a and be done with it. So that being said, my bad. What if I had this equation right here? So let's plug in our value of a, which is just 1 in this case. So 3 times, oh, okay. That top part's going to be fun. So 3 times 3, 3 times 3. 3 times 1 is just 3 minus 3. We got 1 plus 6 minus 7. Huh. Well, that stinks. So the 0 on top is not a problem. It's fine to have 0 for your numerator. It happens. The real problem is having 0 in your denominator. Now, we won't discuss 0, 0, if this is undefined or if this equals 0. That's a discussion for another day. Um, but the biggest thing here is that's a problem that 0 is in the denominator. So while I write this again, this goes into what I said like last time. I'm like, hey, calculus is going to have like these weird concepts you're going to have to learn, but a lot of it is going to be just algebra, just manipulation, moving variables around, doing a bunch of multiplying, dividing, all this fun stuff. And this is where it comes into play because we're about to factor. If I plug in my value of a, I get a breaking of the first commandment of mathematics, divided by 0. Terrible thing to do. Never do that. But can I reduce this, simplify this a little bit? So that numerator, what can I factor out? Correct. I can factor out a 3. What about the bottom? Oh, an easy trinomial. A is equal to 1. I will do this one time. In case you forgot how to factor, I won't spend the rest of the time showing how to factor. I actually have videos on my YouTube channel if you forgot how to factor, so that is there for you as well. But you can skip this part right here if you know how to factor this. We're looking for two numbers that when you multiply get you -7, but when you add get you +6. So then we look at the factors of 7. 7's prime, so just got 1 and 7. Nothing too crazy there. Nothing too crazy, thankfully. So then we're like, okay, two numbers when you add to get you 6, and two numbers when you multiply to get you -7. Clearly needs to be a +7, -1. So that means here, this bottom part, if we have, sorry, I'll write it here actually. So then if we have two numbers that multiply to be -7 and added to be +6, we can write that as x plus 7 and x minus 1, which is good. Again, x plus 7 and then x minus 1. And hey, look what we can do here. What's common? What can we cancel out? You have an x minus 1 we can cancel out. And so with this here, I can now say this is 3 over x plus 7. So when I'm writing this limit, I say the limit as x approaches 1. Instead of saying all of this, I can now say 3 over x plus 7. And hey, this is a lot better and nicer because what happens when I evaluate this at my value of a? Oh, that's not good. Let me go back to here. Perfect. When I evaluate this on my value of a, we get 1 plus 7, which is 3/8. Now, we won't worry about wholes, discontinuities, especially at x equals 1 right now. But for right now, this is saying, hey, whenever you plug in your value of a and something's wrong is happening, like, you getting 0 on the bottom, let's see if we can reduce anything. In this case, we're able to reduce by factoring and just by reducing and canceling out the things that were in common. So that being said, look at this next example. Determine the limit shown in simplest form. So x squared plus 11x plus 28 and x squared plus 4x. So same thing here. What can we factor on top? I'm not going to go through all the examples of how to factor here. This will be x plus 7 and x plus 4. 7 times 4 is 28 and 7 plus 4 is 11. And on the bottom, I can factor out an x. So x plus 4. And so with this, we're like, oh, okay, that's cool. Just cancel out the x plus 4. And so with this here, I'll just rewrite it so it's a little bit neater. Limit as x approaches -4 of, oh, and I made a big mistake here, guys. Mathematically, I'm fine. Okay, so it's not anything crazy that I did wrong here mathematically. one thing that is so important. If you're not, and this may seem very nitpicky, I know this would be very nitpicky, but if you're not evaluating the limit just yet, you must keep the limit sign. So here I need to make sure I keep the limit sign. This is a great thing. So now again, and I won't edit that out, I'll keep that in. Here we go. Now here I'm like, okay, cancel this out. You need to always keep that limit sign until you finally evaluate it. Of x plus 7 over x. Now I'm like, okay, plug in my value of a, be 3 over negative 4. That's very nitpicky. I know it is, but it's important. It's important. It's just notation. I wish we could get more in depth with that, but for right now, let's just concentrate on this. I think we have 2 more examples. I forgot. So to determine the limit shown below, x approaches negative 3. If I plug in negative 3 here, I get 0 on the bottom, which is disastrous. That's not good. So let's see what we can do here. The limit as x approaches negative 3. Okay, so my numerator, yes, I can factor out a 3. That won't really help us in this case. We need to factor out that negative as well. So we'll factor out negative 3. That'll be x plus 3. And then on bottom, well, you can't really factor using any trinomial method, but they both have an x in common. So we can at least factor out an x. So that'd be x plus 3. And hey, look what happens here. We get an x plus 3 on top and bottom. And so this now becomes the limit as x approaches negative 3 of negative 3 over x, which now means that, hey, we can plug in our value of a, which is negative 3. And I feel confident on doing that. I know that negative 3 divided by negative 3 is just a positive 1, thankfully. Okay, we got 2 more. Yeah, now I remember. So with this here, again, factor, factor, factor. Thankfully, these numbers aren't too bad. These are all pretty easy trinomials. When I say easy trinomials, I mean that the a value is equal to 1. If a value is bigger than 1, got to think back to that grouping method, borrow from brother method, whatever method your teacher taught you. And again, there's videos on my website to help with that. So that top part, x squared plus 2x minus 8. Again, I won't go through all of it, how to factor. Be minus 4, plus 4 and minus 2. 4 times negative 2 is negative 8, and 4 plus negative 2 is positive 2. And with this here, we're going to take out between negative 4x and negative 16. I could take out a negative 4. So that'll be x plus 4. And that is great news for me and for all of us because I'm not breaking the rules of mathematics today. Tomorrow's a different story. But for today, I'm good. So we got x minus 2 on top, negative 4 on bottom. And let's just evaluate this. Evaluate it at your value of a. So you get here negative 4 minus 2, which is negative 6 over negative 4, which is the same thing as positive 3 over 2. Again, it's just a lot of algebra here. And then another example, nothing too crazy here, right? So plug in your value of x, plug in your value of 8 right there, and you see that you get 0 on bottom, which is terrible news. Terrible news. So let's just evaluate this. So I can factor out an x on top, which is nice, x plus 6. Oh, on bottom, remember how to do this? This is called a difference of squares. So your teacher may have taught you plenty of different ways. I kind of always remember that as taking the square root of that last term, which is 8, and then doing a plus and a minus. Again, x squared minus 64 can be factored by using a difference of squares. And so if I wanted to, I could multiply these two binomials right here, and I would still get this term right here. So that's for a different video, difference of squares. Oh, I can't cancel anything now. But if I still plug in my value of 8 here, it's not going to work out. Well, I hate to leave videos on a cliffhanger, uh, but we'll discuss this more in class. What can I say? What can I say? I don't know. You'll see that the answer in this case, I'll just it does not exist. Why? Come to class Thursday to figure it out. If you watch this on YouTube, I'm sorry. But that's all we're discussing today. Have a great week. I will see y'all in class.